Hey, thanks a lot. It's wonderful to be here in, is it called Pesnerburg? Is that the name of the city? So this talk is in a session about sequence alignment, but there's no alignment in this talk. But it is sequence comparison. So let me say something about my collaborators before I start, because I won't remember at the end. This work started about a dozen years ago when I was spending some time at Scalar Genomics, and I think Soren Istrel there in the back started us off on this problem that I thought was going to be very simple and very boring. And we found some non-boring results and worked on it in a few years later when it didn't seem to me that people had taken it up in the proper theme. And finally, to fit in the algorithmic part, there's some work by Andrew Smith, who's an assistant professor at my place, and one of our PhD students, Ehsan. So we'll eventually get to the algorithmic part toward the end. There's probably no need to say genome sequence comparison is an important problem with all the data coming out. We have there's thousands and thousands of complete genomes, huge amount of next generation sequencing data, and using comparisons of the sort I'm talking about here can potentially be used in detecting that there's patterns in regulatory regions. CRMs are very, very popular to study. And in addition, one of the things that people use in metagenomics is they run an assembler and you get these various contigs, and classify the contigs by their small word count, like 3-word or 4-word counts. So this sort of simple idea, which Sam Carlin pushed for years, and I never, once again, didn't sort of appreciate it at the time, turns out to be fairly useful. So statistics and sequence matching is one of my big themes, and we know a little bit about statistics of global matching of sequences. We know an awful lot via BLAST, et cetera. We know an awful lot about local sequence matching. But again, emphasize much less about global matching. I'm going to be here talking about a sequence, and it's 4-letter word count. The quadruple A's, AAAT, and so on, all 4 to the K, K-letter words. And so what about the statistics of short words in a longer sequence? And the words occur fairly frequently under this scheme. They can, depending on the word, can be overlapping or not overlapping. And you can't just apply the number of times W occurs in a sequence. You would think you might use the binomial distribution and the normal approximation. That doesn't work very well because of this potential overlapping. Like if it's quadruple A's, they occur in clumps, and then fewer longer distance between the clumps. But so the number of occurrences would just be the sequence length times the probability of a word. The standard deviation is a little bit intricate to calculate, but once you get it, then the standard normal approximation work. You take the number of words, subtract the mean, divide by the square root of the variance, and you get something that's approximately normal. And I just was talking about one word there, but if we're looking at all words, there's a multivariate version of this where you say take a set of words, it might even be all 4 to the K, K-letter words, and you look at the count vector, the number of times you get word 1, and so on. And then if you divide by the sequence length, this will, that vector will converge the probability of each of the words, and there's a covariance that's computed by looking at the in the diagonal, the variance for each of the words, and then the covariance between the ith word and the jth word. And so there's a multivariate central limit theorem. Just trust me, there is such a thing. And this was first done student of Simon Tavares in 1990. And since there are some PhD students potentially in the audience, emphasize this was never published. It only occurs in publication, I think, in my book where I copied it out of Ron's thesis. So if you do a good piece of work when you're a student, even if you're going to go off and make a lot of money in a high-tech company, publish your thesis. One I think that a few other people in this room know about. So let me come now to the problem that we started with, which has got a long history. So we have two sequences, and we want to compare the k-letter words in the sequences. We're going to take them both to have the same statistical distribution, simple independent letters. And down here, the probability that L letters match is just the probability that there are L A's summed over all the possible letters in the alphabet. And this D2, where we started, came up when people were comparing cDNA databases back in the 1980s. So there was lots of fairly inaccurate sequences, and they would do say the 3 or 4 letter word counts and multiply the count vectors from the two sequences and add them up. Let me see. Here we go. So we take the number of times W occurs in sequence A, the number of times W occurs in sequence B, multiply those two and sum them. So the scalar product, I think, is what it's normally called. Really a simple statistic, not very inspiring. And this would be over the 4 to the k. Now, if you take this and deconstruct it a little bit, remember that multiplication is just a quick way to do addition, right? So you can rewrite D2 as a sum over the ith position of the A sequence with the jth position of the B sequence, and ask at ij, is there a k word starting there that's identical? So you change this sum of products into a sum of a bunch of zeros and ones. These are zeros and ones where you know ahead of time what the probability of a 1 is. It's the probability of 2 k words existing. And so when you put in front of a statistician adding a whole bunch of zeros and ones, they'll think either Poisson or normal. And since these are fairly, if n is getting large, these small words occur fairly frequently, you'd expect this to have a normal approximation, and that's just what we started to do at Scalar. I thought, well, okay, this wouldn't be too boring. We would go through an approximation. And so here's a summary of what I think I just said. We have these indicator functions, which are zeros or ones. Their probability is probably a 2 letters match k times in a row. And there are approximately n squared ways to have these happen. So it should be approximately normal. And there's something called Stein's method that allows us to give bounds on this. And I won't definitely subject you to this theorem, but there's a theorem for multivariate that allows this, and we went through and worked hard and got a calculation that gave the distance between a function of Argyle and the same function that would go with the normal distribution, and the convergence rate was square root log n divided by n to the 1/2 minus 3 alpha, where alpha is some number, that when it's less than 6, get a positive power of n on the bottom, and so the bound would go to 0. And the alpha was to do with the word size. So you may remember from local alignment that when the word size is 2 log n or larger, that you get this Poisson approximation. BLAST will work. So when do you get normal approximation? Well, this is kind of cute. You get it when the word size is less than 1/6 log n. Kind of not. There's a base of a logarithm there I'm dropping out, but that's sort of nice. So less than a 6 log n, normal, greater than 6 log n, Poisson. And Soren had hired a guy named Ross Lippert who came and said, "This doesn't work, Mike." And I said, "Ross, check your code." And Ross, I think, never made a mistake coding in his life, as far as I can tell. So there really was something wrong. And in fact, our bound went away, didn't work when the letters were uniformly distributed. When all the letters were 1/4, it wasn't approximately normal. What? And I don't know if the next slide. So yeah, so what happened up here was when they were uniformly distributed, we were dividing by 0. And so our bound wasn't valid. It could still have been normal, but the bound didn't work then. We didn't notice it at the time. So what's actually happening? Let's just to show you how slightly strange this is. Take the simplest possible case, a 2-letter alphabet, 0 and 1. 0 appears with probability P, 1 appears with probability Q, and we'll count 1-letter words. So there's none of this overlap nonsense. You don't have to worry about that. Things are independent. And D2 is the product of the number of zeros in each sequence times the product number of ones in each sequence. And you can count the expectation. And if you calculate the variance, it turns out that the variance, one of these terms vanishes when P equals Q. And so if P is not equal to Q, the variance is of order n squared. If P equals Q, the variance is of order, if P equals Q, the order is n squared. If P is not equal to Q, the order is n cubed. So something really different is going on. And if you look at this a little more carefully, what you learn in your first course in statistics is you subtract the mean and divide by the standard deviation, right? So let's do that. And if we do manipulate things, you come up with this something times a product and a couple of terms that are open. When P is equal to Q equals a half, these other terms disappear. So here you essentially asymptotically get the product of normals when P equals Q, and when P is not equal to Q, you get just normal. But you notice the normality is coming from how well the statistics of Y compares to Y, how well the statistics of X compares to X, and nothing to do with the interaction between them. So it would seem like it's a pretty stupid statistic. We wrote a paper saying that. And it ended up in the interim that not anybody seemed to read why we thought it wasn't very effective. So when we came back to working on this, we wanted to do is take this D2 statistic and transform it so it would have more statistical power. And that I also thought would be a really easy job for a postdoc we had. And we're still working on it. So my judgment in these things hasn't been too accurate. So, okay, so what did we took the word, this is the number of times W occurs in X, subtract its mean, and do the same for the Y. And so our centered D2 is just the sum of these products where the means have been subtracted. If you expand D2, you get the centered plus terms to do with Y plus terms to do with X plus a constant. So you can kind of see so in the uniform case, these guys here are vanishing. They don't have any variation. So if you want to understand this, think if that's always 1 over a constant, then this thing is a constant. Has no variability. And the same thing here. So that sort of explains a little bit better what's happening there. Then we hit on a statistic that our friend Larry Shepp had published something about in 1964, which is even before some of you younger people were born. And so X and Y are normals, and they have their variance is sigma squared x, sigma squared y. And x times y divided by the square root of the sum of the squares is again normal, which has a computable variance. So the reason we like the look of this is that it's self-normalizing. And so our Shep statistic has in it these centered terms divided by the square root of the squares, sum of the squares. And we add over all the 4 to the k words. And finally, we take transform the centered version a little bit by dividing by something that's trying to be a quick calculation for the product of the standard deviations. Okay. So, all right, so how do you say, so it's easy enough to write this and say, I think it's better. But how do you do a calculation to show it's better? You can say, well, let's look at its statistical power, by which we mean the probability of rejecting a false hypothesis. So what's the chance that if there's, say, these sequences are seeded with a pattern in a certain way, that you'll decide that the null hypothesis of no difference has been violated. So the larger the power is, the better. And the null hypothesis, they have the same distribution. The alternate hypothesis is they don't. And we parameterize this we do this 2 ways. The first one is really the simplest possible way. Say you take a 5-letter pattern and you just randomly insert it into both, or replace 5-letter positions in both the sequences with that word. So this would be about the easiest possible alternative hypothesis. The one you'd be most likely to nail, because it would inflate that count for that word. So here's a slightly more challenging alternate hypothesis. We do the same thing, but we go along, and at random points in the X sequence, we take that 5-letter word and replace the corresponding letters of the Y sequence. And so this time, there'll be different patterns that are being transferred. But clearly, a lot of similarity between the sequences, but just much harder because you're not inflating one word count over and over again. So in these power studies, we take a level of significance of 0.05, do 10,000 pair of sequences, and that's where we get the test statistic for rejection of the null hypothesis, and then we look at the number of times we reject the null hypothesis under each of these alternatives. And so I'll just show you a couple of slides for this. This is power. So this is the length of the sequence this way. So you're getting more and more and more longer and longer sequences. You're getting more and more data. Okay. And this one is power, and ideally you would like it to go up to 1 and get there. So all of these get to 1. This is D2 squared star. This is the Shep, and this is D2 itself. So kind of as you expect. We expected to do somewhat the same picture for the Model 2, and this is where the surprise came in. So for Model 2, this is D2 star. It climbs up, and here's sequences out to 12,000. And then it just completely levels off. It doesn't go to 1. It gets to somewhere a little less than 60% of the time. So if you go along and collect data forever, you only have a 0.6 chance of deciding the null hypothesis is not true. More data does not help. And D2 Shep is a little worse than that. What's really interesting down here, take D2 itself. You start out, and the more information you get, the worse off you do, which is really, which is a nightmare for a statistician. And these asymptotes, we actually have theory that I can show you formulas, and we have theory that agree with the simulations.
This is the guy who doesn't write bugs?
Excuse me?
This is the guy who doesn't have bugs?
Yeah. Oh, this was the postdoc, but yeah. Yeah, so at any rate, this really puzzled me. So okay, what do you do next? And Oh, and there's actually, it doesn't quite show it here, but there are examples where D2 goes below the 5% line that we did the simulation with. So it's even worse than tossing that coin. Anyway, so you can see why I found both these rounds fascinating. Stuff showed up that I didn't expect. It was pretty cool. I gave a version of this talk with a lot more formulas in it somewhere else, and Pavel asked something about normalizing the statistic, and I told him I thought it was just duals. But in fact, this is Fengshu Sun's work. He did some normalizations, which I frankly don't completely understand, but it says they normalize things such as nucleotide frequencies, length of reads, and numbers of reads. And these normalized statistic turned out to be much stronger with doing phylogenetic trees and so on. It was really quite impressive, actually. So it was a good suggestion, Pavel, although it completely sailed by me. I don't want to go into this, but at any rate, there's some progress there. And this is also Fengshu's observation that he managed to fix this business where the power doesn't get better or even could decrease by doing the following thing. And I'll show you a slide for this in a moment. Let me try to talk you through it. So let's take our say, D2 star similarity measure. And this M star is the M star ij here is the similarity between the block of length W starting at I and the block of length W starting at J. So I think his observation was the power increased and then it leveled off. So you just work on the front part of that and try to leverage that. So, okay, X star I, as you take an I window up on the A sequence, and you look at all of the windows down at the bottom and pick the score that goes with the biggest one of those comparisons. So that's for each there. And then do the same thing for the windows, starting with the window in the B sequence. Look at all the windows in the A sequence, pick the largest score, and sum those up. And in fact, you can prove that this has asymptotic power 1, so at least he's improved that. Here's a picture for that. So just what I hope I just said. Take this window, look at all possible windows down here, take the highest score. Pick this window, take all windows up there, take the highest score, and then add those up. But this, of course, is a complete disaster. I haven't talked about algorithms until this point. But why did people like D2 back in the 1980s? Because they could compute it in linear time. You read the sequence, you know the k-word count, and you multiply the two vectors together and add the numbers up. He just took this and made it a quadratic time algorithm, which has no appeal at all, right? Oh my gosh. So there's an algorithm problem. And I don't want to try to deal with this, but why don't we just go back to the local alignment, thinking about in the days of Peter Sellers and so on. And so I'm going to define a local word count statistic here. We'll take all windows of W between the two and look at the maximum score of all those possible n squared. I'm not adding them up or anything else, just taking the I and the J that have the largest one of those scores. Can I do anything about computing that faster than n squared time? So here we have the input are these k-mer, k-word count vectors, and the output we want to give the pair of vectors of the maximum dot product, because that's really what this scalar product is, right? Length of the two vectors times the cosine of the angle between them. And this is Andrew and Hassan's work from here on. So it's a string problem, but it's not like the ones that most are used to, because the order of letters is gone, and order doesn't count very much. And I always had in my heart that these sliding windows would help us. And Andrew quickly said, no. So, of course, if we slide the window along, the counts will only differ by 2, And you can definitely learn something from overlapping windows, but it doesn't get us very far. If you look at the sequence length and you divide by, just break it into non-overlapping windows of size W, you'll still get an n over W squared. So you still have quadratic. So it doesn't, you can study this, but it's not going to get you very far. So so we're going to steal something from computational geometry. So I have points in a high dimensional space, and here our dimension is 4 to the k. Remember, so you're just count vectors. Something called cosine similarity has been used in text indexing and retrieval, and is pretty cool, actually. Also, I guess we're kind of stuck with similarities here. Back to Pavel's thing, we don't have a triangle inequality, so with similarities you can't help that, and so these text retrieval things are thinking about points that are on the surface of a sphere centered at the origin. And the pair of points of the maximum dot product is the pair of points with minimum distance. So if we click there, we can get somewhere. And let's see. So now we have 2 sets of points. If the points, say from the A sequences are red, and I think that's blue, right? I'm reasonably colorblind, so if the B sequences are blue, and now if all the A sequences were in this disk, all the B sequences were on that one, so bichromatic is the two colors going with the 2 sequences. The maximum dot product is equal to solving bichromatic closest pair. And back to what we said. Red and blue are the set of count vectors from local windows from the first and second sequences, and we have 2 of these vectors of this length. So the distance between them is the length squared red, length squared blue, minus 2 length red, length blue times the cosine of the angle between them. So the pair with the maximum dot product has the closest distance, and we're interested in finding the closest theta. Closest angle. Okay, the input, and you'll see in a minute why I'm taking this set of M hyperspheres. I'll come back to this, and it'll be hopefully very clear why we're doing this. But all these hyperspheres are the origin. We'll figure out what M is after a while. The first hypersphere is the closest vector to the origin. Rho greater than 1 is going to be our the performance bound, the approximation ratio. And we build these spheres up by multiplying the previous sphere radius by the square root of the performance ratio. And what we're going to do is for each guy in say the red sphere, we're going to project it into the largest radius that's smaller than it. Here's a picture. So we're going to discretize this problem. Here's our red guy, and we project it down to the next sphere below it. So the whole problem would be, here's where you're starting, and then you've taken and projected all those guys into these shells. So we do this separately for the A sequence and the B sequence, the red and the blue. And there are M squared subproblems. And for each of these subproblems, the next slide doesn't show that. So, thought I had a slide. So each of the subproblems, you pick a radius from red and a radius from blue. And all of those guys have the same absolute R, absolute B. And so the maximum product is the closest angle between the two of them. So for each of these subproblems, you look for the cosine of the smallest angle, and that solves this closest pair problem. And then over all these m squared, you keep the one with the minimum distance. So the right, quote, the right choice of the number of spheres has to do with the logarithm of the window size. And this from computational geometry, there's a probabilistic algorithm that has complexity n to the c, where c is less than 2. And you can solve this problem. And I think this should be m squared nc, but I may be wrong there. So at any rate, we can, the procedure I described, you can show that you can do local alignment free based on D2 or D2 star in big O of, I think it's m squared n to the c. So we got it below quadratic by leveraging on this other problem. So this method that I'm referring to uses hashing and has already been used around computer science. So how much faster does this go? This is the naive algorithm, the n squared algorithm, and this is the approximation algorithm. So it goes up quite a bit less. Thank goodness. How accurate is it? And here, again, you have to have something to measure it against. So we measure it against a really simple alternative, having a planted fixed motif. And we take that motif and plant it in a randomly selected window in each sequence. So we pick the pattern we're going to stuff in there. It's the same pattern every time. And we randomly pick a window in the A sequence, randomly pick a window in the B sequence, and load those up. So it's not a very hard, we should be able to find this, but we need something. So the null hypothesis is that it has density, that it's not there at all. Alpha equals 0. Alpha is the density of how well you stick it in. And the numbers I'm going to show you come from sequence of length 100,000, windows of length 1,000, and it's a 5-letter word. Now, how do you? I know this morning when people were talking about this method got 98.7% of the genome and so on. What that really means, that's kind of a complicated thing to explain carefully what you really mean by that. So here, what do we mean by accuracy? So if I wish I could see all these colors and I could accurate description, but suppose this is the window that's seeded. This is the window that the algorithm finds as the maximum, location of maximum. And so you look at the length that's common to both of them, and you divide by the length of their union. So if you were perfect, one was on top of the other one, those would be identical and it would be 1. If they're disjoint, the top would be 0, so SD would be 0. So it's a number between 0 and 1. And we do that for what's the pair that's found. So we do that in each of the A sequence and B sequence, and we multiply those fractions. So that's the number we used. And so at a 4% seed, the naive algorithm gets 0.13. We get 0.08. At 5%, 0.81, 0.81, and so it works pretty well when it's seeded a reasonable level. I could show you something about the distribution. These are just the averages out of, I think, 20 simulations that Ehsan did. And if anybody was interested, I could show you that. So this is kind of a nice simple example where a nice simple, easily stated perhaps, computer science problem arises out of the need to do sequence comparison. It's probably not the end of the interesting things to find about this, but I think I'll stop my talk here. Thank you.
Questions? Is it the larger the K, the more accurate?
This is, let's see, there's no inaccuracy in this. They're just random sequences. And this is the length of the underlying sequence.
But when you apply to the genome or something like that, right? Do you find similarity?
How's that? When
The
you,
genome, the genome sequence. Because I know that you're talking about random sequence.
yeah.
You apply the biological.
Yeah, sure. I mean, of course, that's what we're interested in using this on, for sure. But the question is, I like this problem because it's local alignment, et cetera. How useful this exact statistic is in real sequences, I don't know. So we're sort of.
Because some people study genomes by using the Markov chain or something like that.
Sure.
So they're not related. Not particularly. But you could run this analysis through for non-independent sequences. It all works if they're Markov sequences. So that's not a problem. But its practical use, I'm cautious about. Yes.
I have a question about the background about the word counting strategy.
Sure.
If I get it right, when you do the combination to form a word, it just reduces the scale by a constant number. The nature of the problem itself is still the same when you compare those letter by letter or bit by bit. Is that correct?
Say it again. I'm not sure.
So suppose you have a few sequences.
Yes.
Based on the letter.
Yes.
Now you say, well, let me form the word.
Oh, okay. Yeah.
And to me, it's like word is kind of coding.
Yeah. I mean, people have done that. They've gone along and rewritten the sequence where the letters, instead of 4-letter alphabet, they're a 4 to the K letter alphabet, and so on. Yeah.
So then.
But
the nature of the problem is still the same.
No. I mean, it isn't, because here you're looking at composition. So order doesn't count. Whereas when you're doing alignment, a match, the matches, we know they have to occur in order and they can't cross. In this analysis, the matches can cross.
Oh, so there's no order information?
There's no order information at all. There's no order information. And so you're just taking this letter in your condensing, and you're drawing a line to every letter down there, and you're doing that everywhere. Okay, yeah, thank you.
How far it can cross?
How's that?
How far it can cross? Yeah, the size of the word, the length.
So that was that stuff I talked about at the beginning. When the word, so that sort of defines small. That 1/6 log n or smaller, get one statistical regime. If K is big enough, then you're doing local. Then you're really doing blast type matching, right? It's Poisson. So there are different statistics.
So as I understand, when you use the term sequence comparison, the sequence is fast,
Well, the biologist gave me a okay. Yeah, so my answer would be the biologist gave me a sequence, I did something to it. That is, I did this counting.
But biologists now can give you a chromosome length of several megabase pairs.
Oh yeah, yes. And so that so
call it the sequence spectrum.
Yeah, okay, sequence spectrum. Yeah. The sequences have vanished. I agree. Yes.
Of course, you can have two sequences with the same spectrum that are radically different.
Yes, definitely.
So depending on the Markovian nature
absolutely.
of the generation.
Absolutely, and the Eulerian path thing tells you something about that. Percy Diaconis has a student named Zaman who did a essentially using the Euler-De Broglie thing back in the around 1980 or so, did a paper generating random sequences that have the same k-letter statistics. Yeah, it's very, and there can be a lot of them. Yes.
Some of those issues can they be addressed by not sliding the window, but randomly and independently picking up?
So that's a good question, because you look at what Feng Shu did. He just took them all, right? Stuffed them together, and got a good result out of it.
The reason I'm asking is, if all the errors are together, clustered together, a sliding window may fail, whereas just a random selection may be able to pick up.
Right. And so, one of my questions to him was, well, why didn't you just take the sequences and take the first W window and do the comparison? Take the second one and do it. Would that work? And of course, if there's some organization to how the letters and sequences are coming, that might fail. Good question.
Any more questions? Let us take